We're going to explain how to parallelize a simple Python loop. Imagine you have a loop that performs the same operation on many different pieces of data, like processing images, analyzing sensor readings, or crunching numbers. If you're running this loop sequentially, it can take a long time, especially with a large dataset. Parallelization allows you to split up the work and run parts of it simultaneously on multiple cores of your computer's processor, significantly speeding things up. There are several ways to do this in Python. Let's explore a couple of them. 1. Using the multiprocessing module. This is a built-in Python module specifically designed for parallel processing. It creates multiple processes, each handling a portion of the loop's iterations. This is good for CPU-bound tasks where the processing is limited by the speed of the CPU. We'll create a pool of worker processes and use the map function to apply a function to each item in an iterable, spreading the work across the processes. Example: import multiprocessing with multiprocessing. Pool processes 4. As pool, results equal pool.map, my function, my data. Here, my function is the function applied to each item in my data, and 4 specifies the number of processes. Adjust this based on your CPU cores. 2. Using concurrent.futures. The concurrent.futures module provides a higher-level interface for both multiprocessing and threading. Threading is useful for I/O-bound tasks, where the program spends a lot of time waiting for external resources like network requests or disk operations. With concurrent futures, you can use process pool executor for multiprocessing, similar to multiprocessing pool, or thread pool executor for threading. This offers a more streamlined and consistent API compared to directly using the multiprocessing module. Example: import concurrent.futures with concurrent.futures. Process pool executor. As executor, results equals list. Executor.map, my function, my data. This is cleaner and generally preferred for simpler parallelization needs. 3. Understanding limitations. While parallelization drastically improves performance for many tasks, it's not a magic bullet. The overhead of creating and managing processes can sometimes negate the performance gains, especially for very small datasets or operations with minimal processing time. Also, if your loop involves shared data that processes need to access and modify simultaneously, you need to carefully handle synchronization to avoid race conditions and data corruption. This often involves techniques like locks or queues, adding complexity. Finally, some operations can't be easily parallelized. For example, a loop that depends heavily on previous iterations' results. In summary, Python provides easy ways to parallelize loops using multiprocessing or concurrent.futures. Multiprocessing is best for CPU-bound work, and concurrent futures offers a more versatile, easier-to-use API covering both multiprocessing and threading. Remember to carefully consider the nature of your task and the potential overheads before using parallelization, and always address potential issues related to shared data access. Choose the method that suits your needs and dataset size for optimal results.